Hello and welcome to the video lecture for lecture 21. Here we're going to cover sections 7.1 to 7.3. This is going to be a couple of sections in this chapter, in chapter 7, where we're going to introduce the angular variables. So it's going to be a lot of new terms. We're also going to do a few examples that kind of highlight what we're going to do with those variables. Okay, but I'll kind of mention that, give some caveats and what you should be focusing on and thinking about as we go forward. Okay? And of course, this is introducing chapter 7, which is all about rotational motion. But it is the first of 2 chapters on rotational motion, which is unusual. We haven't really spent 2 chapters on a topic before. So that's kind of going to be kind of overshadowing a lot of things, that the fact that ideas are going to continue to kind of be revisited and introduced throughout, quite a few sections. All right, but with that caveat and warning out of the way, let's get into the content, okay? So, key terms. Well, first we want to define something so important. What's the difference between translation and rotation? And on that note, what's the difference between tangential and radial, right? Because these are terms we're going to throw around a lot, but what do they mean? Okay, so translation is motion along a line. It is described in terms of x and y. And it doesn't have to be a straight line. It just has to be along a line. All right, so a curved path, as long as we're describing it in terms of x and y, is still translational motion. It's translation. Okay, on the other hand, rotation, or rotational motion, is motion in a circle. It is described in terms of theta, and we choose radians instead of degrees as our way we're going to generally do it. Doesn't mean we're going to stop using degrees. We're still going to usually talk about angles in terms of degrees, but when we talk about things spinning and how much they've spun, we'll generally use radians. I know it's a lot of back and forth between radians and degrees, but that is the habit, okay? It's my habit, it's the book's habit. You got to get used to it, all right? But anyway, that's rotational motion, right? So that's fundamentally different, right? Because it's not about moving side to side. It's about spinning while staying in place potentially, okay? Okay, on the other hand, tangential is an axis, it's a direction, okay? So it's not a type of motion. And it's parallel to velocity, because velocity is always tangential to the direction, okay? And it's perpendicular to the radius for circular motion, all right? On the other hand, radial is, again, a direction, but it's one that's parallel to the radius, okay? So you've got 2 things that are more like directions. They're like x and y, okay? It can be described in terms of unit vectors, okay? Whereas translational rotations are types of motion, all right? So I've chosen to highlight a lot of this with an example figure over here. I'm going to populate it with a lot of information. You ready? Okay, here we go. So what's going on here? All right, quite a few things. This is a disk that's speeding up, so it's not spinning at a constant rate. All right, it's got some fixed center. At the center of that disk, we can look at a translational axis in terms of x and y. The disk has some radius r. But at any point along the perimeter of the disk, if we look at these little pink dots, we can consider the motion of those pink dots not necessarily in terms of x and y, but in terms of the other axes that we just introduced, radial and tangential. It's really helpful to do that. Why is it so helpful? Well, for a number of reasons. First of all, the tangential direction is the direction the velocity always points in, so right away that makes that direction significant. And the radial direction points right towards the center of the circle, which happens to be the direction of a type of acceleration known as centripetal acceleration, which also is sometimes called radial acceleration because it points along the radial axis. So let's look what's going on here, right? Because I set this up as an example of sorts. So we have here at t equals 0, v naught equals 0, right? So this is a disk that hasn't started to spun. So at this particular point in time, this point along the perimeter, as well as any point along the perimeter, isn't in motion yet, okay? But there is going to be an acceleration because the disk is just starting to spin. So if we were to zoom in on this little pink dot, we would see that it's jolting into motion, thus giving an acceleration in the tangential direction. That's its initial acceleration. We would call that acceleration a tangential acceleration because it's entirely tangential. Okay? Now what happens at some time later? Well, t at 1, 1 second, 1 minute, doesn't matter, but sometime later, things have changed. The velocity now is non-zero. The whole disk is in motion, thus so is that little pink dot. Furthermore, that means that we have now 2 types of acceleration. The disk is continuing to spin up, speed up in its spin, so there's still a tangential component of acceleration. But now, due to radial acceleration and the fact that this point isn't moving in a straight line but is turning, there's a second type of acceleration called radial acceleration or centripetal acceleration. That makes the total translational acceleration, because this is, after all, r and t might as well be x and y, okay? Because they're still translational axes. They're different translational axes than x and y, but they're still translational axes. So the total translational acceleration is this value here, a, with the subscript 1 because it's at time 1. So we see then that the translational velocity is tangential by definition, but now we have two components of acceleration. All right, but now look, I have more information over here. I have all this stuff that's written in sort of this cyan color. Well, what's this? Well, these are the angular terms. Right now, they might just look like some random Greek letters, but it turns out that they have meanings which I'll introduce on the next page. Omega is the angular velocity, alpha is the angular acceleration. And since this disk is spinning up, the initial the angular acceleration is never zero because the disk is speeding up. Furthermore, it's not zero at time 1. However, when the disk starts, when it's just starting from rest, the actual initial angular velocity, which we represent by omega, is 0. So in other words, when v is 0, omega is 0. But alpha is never 0 because the disk is, after all, spinning up. Okay? So I keep saying that, but I mean speeding up, right? And then, but they're both not 0 once the disk is already in motion. Both being both of the rotational terms. So these terms are not translational, fundamentally not translational. This is a whole new way of describing motion. These are rotational kinematics. All right, that's by far the newest idea. Splitting up acceleration, having new components, that's new, right? But it's also similar to things we've done before. Talking about rotational motion is fundamentally different, right? It's not meters per second anymore, it's radians per second. And it's not meters per second squared, it's radians per second squared. All right, and if we look down here, right, we could maybe assume that angular acceleration is a constant. We're going to see a lot of examples of that. The whole next lecture is going to be focusing on that particular type of example. Furthermore, we're going to assume that the disk starts spinning at time equals 0 and continues to speed up from that moment onwards. And that is reflected in the vectors and the information on the rest of the disk. Okay? So again, this is a disk that's fixed in space, right? It's got a fixed axis and it's spinning around it like a potter's wheel or something, all right? And that means that it has rotational motion as a whole. The whole disk can be described by the values of omega and alpha, whereas only individual points can be described by the variables of radial acceleration, tangential acceleration, and translational velocity. Okay, and of course, when I say radial acceleration and tangential acceleration, I could say, although it's a mouthful, radial translational acceleration and tangential translational acceleration. Okay, all right, so let's get back to that idea of the fixed axis because that's our next key term here. This is a rigid body fixed axis rotation. That's in fact what's happening here. All right, so this is rotation where the shape of the rotating object doesn't change. That's the rigid part. And the axis of rotation is always located at the same location on the rotating body. All right, so this is everything that we do in this class. We never break those rules. If we do, it's very, a lot of considerations to make that are well beyond the scope of the class. All right, now this actually is going to be more front and center in the next chapter because then we're going to get into the dynamics of rotation and something called torque and actual rotational kinetic energy, but we're leaving that all for the next chapter, okay? And I'll give that caveat again in just a minute, but I'll try not to repeat myself too much. But it still is a term I want to introduce because it certainly does apply to the picture that I used as an example just now. All right? All right, we got a couple more, right? So we have the angular velocity vector. Okay, well, that's omega, all right? That's the formula you're going to see on the next page for key formulas, but here's kind of the definition. It is defined as omega, it is a vector, and it's defined as the change in theta over change in time, at least its magnitude is, okay? It is a rate of change of angular displacement. Angular displacement is that theta right there, right? Now, so that's an angle, and it is, but it's also displacement, because if I spin a wheel through a half turn, that would be an angular displacement of pi radians. Now, we're probably used to calling that 180 degrees, but we want to get used to thinking of that displacement as pi radians, because we're going to be using radians a lot, okay? The direction of omega is found with your right hand, okay? That's called the right hand rule. It's not going to be a big deal in this class. It's a big deal in the calculus sequence classes. Not so much in this one, but it's still relevant. And what we want to think about with it is this picture over here. This is meant to be 3D, kind of looking at maybe the same disk, but from the side. This would be, continuing with that 3D idea, this would be like an axis kind of coming up from the middle, right? And the whole thing's tilted. So now take your right hand, humor me here, and fold your fingers along the direction of the curve. Well, you'll see that your thumb points this way, doesn't it? Naturally. All right, well, that tells you if the disk is spinning this way in the counterclockwise direction, then your thumb points in the direction of angular velocity. All right, just like that. All right, that tells you the direction of the angular velocity. Now you might be like, wait, why is that the direction of the angular velocity? Shouldn't it be the direction of these green arrows? But which one would it be? Would it be this green arrow? And these are curved, right? They're not vectors. And because of that, because we need a vector to have a definitive direction, it's defined as perpendicular to the plane of rotation. Right? So this disk is the plane of rotation, and the actual angular velocity vector is defined perpendicular to that plane. It's an odd idea, right? But it's how we give a definitive meaning for angular velocity, right? As a vector. Furthermore, we have the angular acceleration vector, right? Defined as this. It's going to be a vector is equal to the change of angular velocity over time. The units will be radians per second squared. We'll see that quite a bit. And it represents the rate of change of angular velocity. The direction of that angular acceleration vector is along the same axis as omega. It's along the axis of rotation. That's usually what we call this, okay? And it isn't necessarily parallel. It can also be anti-parallel. And specifically, it is parallel if the disk is speeding up, say like in the example above. But in this case, I want to consider the opposite case, a slowing down disk. And in that case, it's anti-parallel, because it's actually trying to slow it down. So you'd use your right hand to represent the direction of velocity, and if you know your disk is slowing down, then you know that angular acceleration points the opposite way, okay? As shown in this picture. Okay, so there's kind of a very pictorial representation of angular velocity and angular acceleration, but let's get more into how we actually see them come up in equations that we're going to be using to solve problems. All right, so the key formulas. Okay. So let's go through them. Again, this is going to be an overload of new terms, but ones that we'll continue to have practice with over the next few lectures and the next chapter. Okay, so they're going to stick with us. All right, so first key term here, angular displacement in radians. All right, that's theta. All right, so every time we talk about angular motion, you see a theta, you need to assume it's in radians. Now, you're going to see examples in this section as well as many other sections in this chapter. We're going to have tilted things, or we're going to be talking about pendulums, and we're going to talk about that pendulum released from a certain angle, and I'm going to give you that angle in degrees, okay? So we're going to be using both degrees and radians depending on the context, okay? But here, definitely radians. S is the arc length in meters, all right? That's how far you've gone along that circular curve. We're only talking about circular curves here, not some other shapes like ellipses or something. So S is the arc length along the circle, all right? And then R is just the radius of the circle, also in meters, okay? Always circles, all right? Next thing here, we have the definition of a revolution. Shortened here is rev. I do that a lot. So one revolution is of course 360 degrees, or 2 pi radians, which is a good reality check there of how to convert back and forth between radians and degrees. All right, so rad, short for radians. Okay, now we have our official definition of angular velocity. This is instantaneous angular velocity, and is the limit of the as time goes to zero, as the change in time goes to zero, of the change in angular displacement over the change in time. Of course, average angular velocity would just be getting rid of the limit, and then you would define that with a bar above to denote average. All right, next up, angular acceleration. All right, same limit definition. As we go to really small changes in time, then we approach the instantaneous angular acceleration, and it's the change in angular velocity over change in time. All right, so the units of angular velocity would be radians per second, and the units of angular acceleration are radians per second squared. Okay, so these are our two big new kinematic terms, okay? And we'll call that as much in the next lecture. We'll talk about really, kinematic equations for angular motion. Now here's the thing, besides that next lecture where we do get into really, doing kinematics with alpha and omega, alpha and omega are really mostly going to wait until the next chapter. Because after the next section where we, in my next lecture where I do a few examples of constant angular acceleration, then we go on to like talking about banked turns for cars, and and these things called conical pendulums, and then we talk about gravity and circular motion of satellites using a lot of the same ideas, including centripetal acceleration. But here's the thing: all of that doesn't use alpha and omega. So it's kind of like we introduce them and then we forget about it for a while, but then in the next chapter, in chapter 8, they're going to come back. So keep that in mind. They're relevant here, but they're going to be more so later on. Okay? Now, what we really want to consider for this section, now to finally get to the main focus of the section, because this is an introductory section, which means it's got a lot of upfront information. right? That's the nature of it. By the time I always get to the last lecture of the chapter, it's kind of like, oh, here's a bunch of examples. But right now we got all that upfront information that you gotta, pay attention to, hopefully, right? So here's the thing. We're finally going to get to the equations that are really going to be front and center for the next examples you're going to see, all right? Because we will eventually get to examples. And so these 4 sets of equations are the ones I want you to focus on, right? First up, well, this is just velocity, okay? This is translational velocity, the same old v, that hasn't changed, okay? Now we're going to define it as r times omega. So what that's saying is that velocity is equal to radius times angular velocity. Likewise, if we could solve for angular velocity and say it's v over r. So that allows us to go back and forth between translational velocity of a certain point on a rotating object and relate it to the angular velocity of the object as a whole. Because that's the thing. That's the rub. That's the idea that you need to get and can be tricky to get at first pass, because you might be thinking, oh, there's all this information, I'm going to ignore something. Don't ignore this. Angular velocity describes the object as a whole. Translational velocity describes one point on that rotating object. Likewise for angular acceleration. Object as a whole, translational acceleration, one point. Okay? Because look, translational velocity is dependent on radius. Omega is not. We've divided by the radius. We've gotten rid of it. Okay? All right. So here's our first key equation here for this chapter, or this section, this lecture, excuse me. Right? Next up is the definition of tangential acceleration. You saw it on the figure on the last page. How do we define it? Well, first of all, we can use the subscript t to denote tangential, and it's defined as r times alpha. Okay? It's defined as the radius times alpha, and what is alpha? The angular acceleration. Okay? Well, okay, so that's great. That's tangential translational acceleration. There's that mouthful, okay? But then there's also the radial component of translational acceleration, or radial translational acceleration. Well, that one is just a sub r, and that one, also called centripetal acceleration, maybe a more common term for it, okay? Well, that, and we talk about centripetal forces quite a bit in 2 lectures, okay? So centripetal acceleration, by definition, is v squared over r, right? Not gonna give you a derivation of it, but it's the translational velocity divided by the radius. So that's interesting because that tells you that the faster you go, your radial acceleration grows pretty fast because it grows with the square of velocity. But we can do a substitution here, and we can take our equation up here, replace v with r omega, which then cancels out one of the r's in the denominator, and we're left with omega squared times r as another way of expressing radial translational acceleration. So then we see that our 2 components of translational acceleration are dependent on the new angular kinematics, right? R alpha and omega squared alpha, and omega squared r respectively. Okay. All right, okay? But the interesting thing about radial acceleration is, depending on the context, we can define it entirely in terms of translational terms, v squared over r, or in terms of angular expressions. All right, okay? Last up is, since these are components, and we saw that they're components on an axis is composed of a tangential axis and a radial axis that, of course, are perpendicular to each other. Well, that means you can form any vector from those 2 components using just the Pythagorean theorem, right? Or using SOHCAHTOA, right? They make right triangles, all right? So this is just the Pythagorean theorem showing that the total translational acceleration is just the hypotenuse of a triangle formed of 2 legs, one being the tangential acceleration, the other being the radial acceleration, all right? Furthermore, I have a note here I forgot about. For objects spinning with constant omega, so constant angular velocity, or for a long time, the acceleration of points is called the centripetal acceleration, okay? All right. So it's usually kind of like the changes where we might call it radial acceleration, but for something in uniform circular motion, then which is a type of motion where it's practically spinning at a constant rate, then we often call it centripetal acceleration. So they're kind of synonyms, but the context matters, all right? And so this is just total translational acceleration. As I was saying, it's the hypotenuse of the triangle. This would just be the vector form of the total translational acceleration with its 2 components. T hat here is a unit vector that points along the tangential axis, and r hat is a unit vector that points along the radial axis. Okay, refer to the figure on the last page to make sense of those axes. They move with your point, okay, because the radial axis always points towards the center of the circle, which isn't always in the same direction relative to x and y if x and y are fixed at that center. Okay, so there's a lot of kind of thinking about some angles there, a lot of geometry at play. So last point here is that these big 4 equations here are the equations that relate translation to rotation. And that is what we want to do with some practice, with some examples. So let's do it. All right, so we have two types of problems here. Problems that involve constant angular velocity and zero angular acceleration that highlight the relationship between angular and translational quantities, okay, because that's what this lecture is all about. Type 2, problems that involve non-constant, okay, so that's the difference. Angular acceleration that highlight the relationship between angular and translational quantities, all right, and this includes pendulums. I mentioned pendulums because pendulums are going to come up a lot in the throughout this chapter and the next, okay? All right, so let's get to the first example. Rigid disk, okay? Oh yeah, that was one of our rules, right? Of radius 1.5 meters, spins about a fixed axis with fixed axis with angular velocity of omega equals 3.91 radians per second. Okay, what is the angular position as a function of time for this disk? Okay, well, here is average angular velocity. All right, but when omega is a constant, we can just drop that average, and then so omega is just, and drop the deltas. Omega is just theta t, theta over t, that is. So now if I solve for theta, that's my position function in this case, angular position function, then it's just omega times t. All right, so then as a function, it'd be 3.91 radians per second times the variable time, times t. All right, so that's a position function. Just like we could say that we have, x equals vt for constant translational velocity. All right, so a simple position function, but in this case, angular. It's good to start simple when we're doing such new ideas. Okay, all right, part B, I ask, how many revolutions does a disk make in 1 minute? 1 minute. Well, let's use our position function. All right, so for 1 minute, we have to convert it to seconds, so we'll convert that over to 60 seconds, and then we find that it makes 235 radians. That is the angular displacement after that much time. But we weren't asked for radians, we were asked for how many revolutions. Well, that means we just need to convert over from radians to revolutions, so we take the 2 pi rad per revolution. So if we divide 235 by 2 pi, we get 37.3. We don't need to round because I didn't ask for complete revolutions, so a fraction of a revolution is fine. Okay? All right, moving on. What is the angular acceleration as a function of time for this disk? Well, omega is a constant, so that means that alpha is just delta omega over delta t, all right, and is 0, right? Because there's no delta. If omega isn't changing, then you have a 0 in the numerator. So your angular acceleration is by definition 0 when your angular velocity is constant. Just how it would apply to translational acceleration. All the same rules that apply to translational acceleration and velocity that we've hopefully internalized from using kinematics for so long apply to rotational kinematics. Okay, so that's good. All right, now part D. What is the translational velocity and acceleration as a function of time for a point along the outer edge of the disk? Okay, so now we need to convert over from rotational to translational terms. So V equals R omega, right? One of our key formulas. And since omega is a constant, V is a constant as well. All right, so then V would just equal 1.5 times 3.91. Simple as that. So it's a constant value of 5.87. And again, that's for a point along the disk, right? If I asked for a point that was halfway between the center and the outer edge, it would be a different number, okay? But I didn't. I asked for a point along the outer edge. That's why I used the full radius of 1.5 meters, okay? And then the radial translational acceleration is V squared over R, which is then just going to be 5.87 meters per second, quantity squared over the radius, all right? And that also gives us a constant value, right? Because everything in here is constant. So the radial acceleration is constant as well. It's 22.9 meters per second squared, all right? Then we're going to go on and define the total translational acceleration using that idea that it is the hypotenuse of a triangle with two components. Well, the tangential component, we know tangential translational acceleration is just alpha times r. Well, alpha is 0, so that whole term just zeroes out. And that means that our total translational acceleration is just omega squared r. It's just equal to centripetal acceleration because v squared over r equals omega squared r, right? Okay? And so then that means that our total acceleration is none other than 22.9 meters per second squared, the same as our radial acceleration. Okay? All right. Why is our total translational acceleration the same as our radial acceleration? Because the disk is spinning with constant angular velocity. Okay? All right. Let's move on. Concept question. The figure shows plots of angular displacement theta for 3 cases of a rotating disk, right? So time on the horizontal axis, angular displacement up there, okay? Notice that angular displacement is actually in degrees here, breaking the rule, all right? But, we always got to break it sometime. But the form of the function is what I'm more interested in, the shape rather than the actual values on the vertical axis. I do care that it's an angle. What value of time does each disk change direction? Okay, well then we need to look at the point where the tangent line is 0, because that by definition would be the angular velocity. All right, because when angular velocity is 0, that's our change. So it's going to happen right here because there's our horizontal tangent line. So -2 for the green curve, 0 for the purple curve, and 2 seconds for the blue curve, because that's where we have horizontal tangent lines in each case. All right? At what value of time is the angular velocity omega 0? At those same times, because changing direction and momentarily having an angular velocity to 0 mean the same thing. Okay, that would apply to translational motion as well, and everything we talked about free fall or throwing an object straight up and tracking its vertical position as a function of time and getting that parabola, right? Same sort of information could be gleaned from that. All right. All right. Part C, for each case, is the angular acceleration 0, constant or non-constant? Well, it's definitely not 0 because theta is not linear. All right, if theta was linear, then that would tell us that it might that omega might be constant. It appears we have the acceleration does appear constant because theta looks parabolic, right? We don't know for sure this is a parabola, but it looks like a parabola, so that's telling us that alpha, angular acceleration, is probably a constant. And for each case, is the angular acceleration positive or negative? Well, it's going to be positive for the green, negative for the purple, and positive for the blue. Why is that? Because the sign of the acceleration, in this case the angular acceleration, matches the curvature. Okay, we've seen that idea before, just for translational kinematics. Okay, so good comparison there between translation and rotation, and just a good figure to make sense of. All right, so now it's a couple more examples. Example 2, what is the angular velocity of a second hand of a watch? What is the translational velocity and acceleration of the tip of the second hand if it is 1.6 centimeters long? Well, let's see. All right, so the angular velocity of the watch is just going to be theta over t, or 2 pi radians per 60 seconds, and that gives us a rather slow speed of 0.105 radians per second. Okay? All right, and of course that describes the second hand as a whole, the whole rotating object. But if we want to find a particular point, which is the tip in this case, all right, then we're going to multiply omega by the entire length of the watch hand. So we'll multiply that angular velocity by the length of 16 centimeters converted to meters, and then we get a translational velocity of 1.68 times 10 to the negative 3 meters per second. Okay, and then we're also asked for the acceleration. Well, the acceleration is just the radial acceleration because it's constant, so we can count on there not being a tangential acceleration. If you want to see why we can count on there not being a tangential acceleration, refer to example 1. Okay? All right, so here we have that it's just going to be v squared over r. We'll plug in our numbers, and then we get 1.75 times 10 to the negative 4 meters per second squared. That's a really small radial acceleration. Well, that means that the centripetal force, and we'll talk about centripetal forces, but you've probably heard that term before, is really small for a second hand. But of course it is. It's not like that second hand is undergoing a lot of stress because of its rotation. It's like, slugging along. Okay? All right, so moving on to example 3. Now, example 3 and example 4 deal with non-constant angular acceleration. That means we're going to have two components of translational acceleration. Let's see what that looks like. Okay? All right, so first of all, part A here. Let's look at the information before I jump ahead. A person is on a spinning amusement ride with a known radius, 9.4 meters. In a period of 5 seconds, the rider's angular velocity changes from a value of 2.2 radians per second to 3.6 radians per second. At the end of that range of 5 seconds, the angular acceleration is measured to be 1.1 radians per second squared. Question A asks, what is the rider's average angular acceleration during the specified time range? Well, that's going to be as simple as just taking delta omega over delta t. All right. And we get an average angular acceleration of 0.28 radians per second squared. In part B, I asked, is the angular acceleration constant? Well, on the information that we were given, we can say no. Why? Well, because alpha omega is not equal to the instantaneous angular acceleration given. The one that we were told was 1.1, and that was the 1.1 that happens to be at the end of the 5 seconds. Well, that means actually it's definitely been speeding up. The angular acceleration has been gradually changing. It was smaller at some point, maybe even 0 at the beginning, but at the end it's 1.1, with the average being less than that. So definitely non-constant, okay, and growing. All right, part C. What is the person's translational acceleration, magnitude, and angle measured from the radial direction? Okay, so this is a big question. This is going to be in both this example and the next example. Okay, so assuming this is for the end of the time interval when alpha is given, I should have specified it more explicitly, but we're definitely going to make that reasonable assumption, which is because that's the only time when alpha is given we can actually solve for it. All right, then we want to find the two components of translational acceleration, a rad and a tan. Okay, this is what they're going to look like on basically a little subsection of the amusement ride. This would be the perimeter of the amusement ride. All right, this is our person. they're experiencing a radial acceleration, and they're also experiencing a tangential acceleration because alpha is non-zero. That means that the net translational acceleration is given by this vector here. We can see that that is obviously the hypotenuse because we can move the tangential translational acceleration back to where we want it and get a nice right triangle. And then the angle that we're asked for is that theta angle right there because it's the angle of the total translational acceleration relative to the radius, the radial direction. Okay? All right, let's do it. So in the calculation, the radial component of translational acceleration is just omega squared times r. So 3.6 radians per second, because that's the final that we were given, times the radius of 9.4. That gives us 120 meters per second squared, rather large value. For the tangential acceleration, it's just alpha times r. Alpha, we were told at the end of the interval is 1.1, right? So we just take what's given, and we take the given radius, and we get 10. So definitely the tangential component is smaller, so I somewhat drew it to scale over here in the picture. All right. If we want to find the total, we'll just use the Pythagorean theorem, and we get that actually with 2 sig figs, it just rounds back to 120. So almost like the tangential doesn't even show up. With three significant figures, it does, right? But we were working with only two significant figures. But we can go ahead and find the angle, all right? And to find the angle, we'll use inverse tangent because it's opposite over adjacent, all right, is going to be tangent. So the opposite is the tangential component. The adjacent, I'll zoom in a bit here, is the radial component. And so there's just going to be 10 over 120. All right, the units cancel out, and we take tangent inverse of that, and we get 4.9 degrees. All right. Now, could I give that in radians? Sure. I think it's easier to visualize degrees. So I would always give this type of angle in degrees. Okay. So let's basically do this again, but do it for a pendulum. It's worthwhile to do it again because, first of all, a pendulum is such an important system, and also because this is going to involve some other steps that we didn't see for the amusement ride. Namely, it's going to involve conservation of energy as part of the setup. And also kind of extra considerations of gravity that wouldn't have mattered for the amusement ride because it was entirely horizontal. So definitely there's an extra level of complexity. This is our final example. So, as is the habit, this is the most complex example. Okay, I did make a dumb mistake and forgot to specify the length of the pendulum. We need that because I'm asking about translational values. So we're going to take it as 1.5 degrees. That was just a mistake on my part. Okay, so first of all, here's everything we're going to consider. We're going to consider, a centripetal acceleration vector. I could have called this radial. I just called it centripetal. We're going to have a total translational acceleration vector. We're going to have an angle relative to the radius or relative to the string, which is the radius. We're going to have gravity. Gravity is going to have components in the radial and tangential direction. The only one we care about is the tangential component. We're going to have the height because we're going to have to consider energy. Because look at the information we're given. We're told that a pendulum is released, right, which assumes from rest, and we can. Every time you see the word released, you have to assume rest, at an angle of 56.5 degrees, not shown. A moment later, the pendulum is at an angle shown of 32.8 degrees with the vertical, okay? So at the moment that the angle is 32.8 degrees, what is the total translational acceleration of the pendulum bob? This is the bob, by the way. And what angle does alpha, the total translational acceleration vector, make with the string? That's an angle theta, phi, that I drew in the figure, okay? So to do that, to deal with the energy conservation as our first step, we have to do a very common bit of geometry that you'll do with many, many pendulums, which is consider that cosine theta is L minus h over L. Well, that would be this right triangle here. So if I think of cosine of theta, that would be adjacent over hypotenuse, so L minus h over L. How do I know that this is L minus h? Well, because the height is h, right? And so that means that this total length here must be L, because the pendulum is going to swing down after all, and the string doesn't stretch. And that means that this side of the triangle is L minus h, okay? So then when I solve for h, skipping algebraic step, h then is L times 1 minus cosine theta. Okay, that is so crucial with so much energy conservation problems involving pendulums. Okay, all right, so memorize that. Okay, so moving on, using conservation of energy from release, so E naught to E being the one that's shown, E naught not shown, we're then going to have that the initial energy is entirely gravitational potential. The final energy is going to be a combination of kinetic energy and gravitational potential because it's not at its low point yet. All right, so then we're going to find that the velocity at the point shown is going to be the square root of 2g times h naught minus h. All right, h being the instantaneous velocity or height shown, h naught being the initial height. Okay, so then I'm going to go ahead and substitute h in terms of theta because we were given theta. All right, and then we could have calculated both h's, right, pretty easily, but I decided to do it more symbolically because it cleans up rather nicely. The negative causes the direction to, or the order to reverse, so it's going to be cosine theta minus cosine theta naught, but you can see that by just distributing the negative here and canceling out the l's. And so then we get then that the final velocity is just 2.39 meters per second. Okay, excellent. Okay, and the velocity is independent of L. All right, it's just dependent on h. Okay, especially because we were given theta for both of them. But we will need L later on. Okay, so moving on, we're then going to use that v and gravity to find what was asked for, which is the total translational acceleration. But let's make a point here. We see the gravitational acceleration right there, in specifically the one that points straight down, has both radial and tangential components. Yeah, because our radial and tangential are defined, relative to where the ball is at this particular moment in time. Okay, totally fair. But only the tangential component actually creates motion. The radial component doesn't do anything. It's kind of like, the gravity doesn't do anything when you're on a flat surface, all right? If there's no friction, then it just doesn't matter, right? Likewise here, this component of gravity isn't going to affect the motion, all right? It will affect the tension, but we're not asking about tension. That's going to be for a later lecture in this chapter, okay? All right, so moving on, we're going to find the total translational acceleration the same way we have, but now neither of these terms are going to be zero. So the tangential term for the first time, well, not, I guess, the second time, isn't going to go to zero, all right? Because in the previous example, it also did not go to zero. All right, so what is going to be the form? Well, the form of the radial acceleration is going to be v squared over L, all right? So that's where we're going to use the v that we solved for up above using conservation of energy. All right, this is where we're going to need the actual value of L. Meanwhile, the tangential translational acceleration is just the tangential component of gravity, or g sine theta. Okay, so we plug in all our values, and there we go. We find that the magnitude of total translational acceleration is 4.17 meters per second squared. That would be the length of that vector right there, okay? And that would be for the bob, right, which is a particular point along the string. If the string was a different length, we'd get a different number, right? That's why the length needs to be specified. Okay, if we want to find the value phi, then we're just going to do exactly what we did before. We'll take opposite over adjacent using inverse tangent and plug in our values for tangential and radial, all right? Okay, and, oh, it looks like I swapped them. I did, typo. So what I did is I put, because it should be opposite over adjacent, so it should be tangential over radial, which I wrote correctly, but then I put radial over tangential. All right, so typo there. I'll fix it in the upload. So take note that this is not right because I swapped the order. Okay, so please look for the corrected value. It will not be 35 degrees. That's too large. Okay, it's going to be a different value than that. Okay, all right, just yep, typo right there. Caught in the lecture. So please take note of it. Okay, so moving on to the final couple questions, which are quite short. What is the angular acceleration? Well, we can find that quite easily now, since we know the tangential acceleration. All right, so the tangential acceleration, after all, is just g sine theta. To go from tangential translational acceleration, a tan, over to alpha, angular acceleration, we just divide by L. Okay, just like going from translational velocity over the angular velocity, you just divide by L. All right, so we just take g sine theta, divide by L, and there we go. We find that we have an angular acceleration of 3.54 radians per second squared, the units of angular acceleration. And our last question here is alpha constant? Well, what do you think before I tell you? You got an answer that you're confident with? Okay, well, no. Why? Because it's dependent on theta. You can see it right there. Alpha is dependent on theta. And that's the fascinating thing about pendulums, is they have a non-constant angular acceleration. And even if they had a constant angular acceleration, that would mean they'd have a non-zero tangential translational acceleration. But the fact they have a non-constant angular acceleration means that they have a very non-constant translational acceleration. All right? And that's a technical term. Very non-constant. Not really. All right, well, I hope that this lecture was informative and was a good, solid introduction to a lot of these ideas that we're going to be working with for a while now. Okay? All right, well, thank you so much for watching, and look out for future lecture videos.